All right, so we definitely talk about the big kahunas, like the big biomolecules, but organic compounds are also important in how we think and feel due to hormones and neurotransmitters that, again, are made up of those same carbon-carbon and carbon-hydrogen bonds. We know that all of them have to have at least one carbon-hydrogen bond, and most of the time we see multitude of carbon bonds and carbon-hydrogen bonds to form rings, of course, chains, branching, as we see here, and also these carbon bonds, or carbon itself can bond to oxygen, nitrogen, sulfur, different things like that. And so guess what? How we learn, our memory, our mood, how calm we are, all these are organic compounds, folks. That's why it's so important. And that's why it's so ubiquitous in so many industries. So what about when we hear organic food? How is that different from organic chemistry? Well, first, organic food are organic compounds, right? And they can have organic compounds sprayed on them. But the organic part of the label is not based specifically in chemistry. It's based in farming practices, right, folks? Farming practices. And so in the field of agriculture, they use the term organic entirely different from the chemical use because everything is based on labeling, food labeling, okay? So for a food or feed product to be labeled organic, there has to be certain agronomic and animal husbandry practices that are followed. So animal husbandry meaning that it's not just about farming food, it's also about farming animals as well. Okay, folks, so that's encompassing it. So this is all about a label. In chemistry, the definition is based on chemical structure and reactivity. So yes, we know it has to have at least one carbon-hydrogen bond. And of course, we know that carbon has the ability to catenate and form all these rings and branches. Okay, so the mix-up really comes from the media and the time we live in. So we rarely think of like organic vegetables, fruits, it's always in the news and stuff like that. So I just want to make sure you know how to distinguish these two versions of the term. Now let's get into another definition word that can get confusing. What is inorganic versus organic chemistry? First, let's start with the definition of organic chemistry from our flashcard that we already made, right? We know we're dealing with carbon compounds that must have a carbon-hydrogen bond. We have there, and can be bonded to other carbons, nonmetals, and halogens. And of course, these are all covalent bonds. All right, so list some examples. Human skin, wood, food, plastic, soaps, detergent are all organic compounds. All right, therefore, organic chemistry, we can just almost do a vice versa or opposite here. Inorganic chemistry has to then deal with compounds that are not primarily composed of carbon, hydrogen, and don't catenate for things like that. Okay? So that means inorganic compounds can contain metals, nonmetals, metalloids. Think of the entire periodic table, right? It can contain all those as well. And it also can have things that are going to form ionic bonds as well that aren't carbon-based. It doesn't have to have carbon only. But we do have inorganic compounds that do have carbon. So you have to ask yourselves, wait a minute, how do I distinguish between like a CO2 molecule versus a CH4 molecule? Why is this one going to be considered organic? And the answer would have to be the fact that this CH4 molecule has at least one CH bond, whereas CO2 does not have any CH bond, so therefore it's not organic. Again, I just want to make sure you know how to distinguish between these two terms. Organic is going to be carbon, okay? That's carbon compounds that must have a carbon-hydrogen bond and be bonded to other carbons, nonmetals, and or halogens, okay? Whereas again, inorganic chemistry deals with compounds that are not primarily composed of that carbon-hydrogen. So it could be anything. Make sure you write this down. This doesn't have to be a flashcard moment because it's just kind of distinguishing, but for you, if you want it to be, it can. Now, before we get into examples of why organic chemistry is so important to study in all the industries it affects, I want to know who came up with this, right? And of course, that's a very loaded question when we're talking about a brief introduction, but we do have some key players. So we're able to distinguish between inorganic and organic chemistry, right? And because we had a solid definition of organic chemistry, we know it was carbon compounds with at least a carbon-hydrogen bond, bonded to other carbons, nonmetals, and halogens. We already wrote down that on our flashcard, so that allows us to make the distinguishment between organic chemistry, or inorganic and organic way easier, right? Having that solid definition is going to help us discern. And our definition is based on the history of scientific discoveries and stories that allow us to learn what we have this far. Not that we're just, I'm coming up with this on my own. No, this all comes from the shoulders of other people who have put in the work. Okay, specific scientists who have gotten us to this far. But in the beginning of getting to where we are now, right, there was not enough scientific data to understand the difference between like something organic and inorganic. It was all boiled down to here's things that are living and here's things that are non-living. It was really thought that only living things can create living compounds. Okay? And the way that these living things create living compounds is due to a vital force. And may the force be with you, right? A vital force. This vital force is what's called a life force that they thought is why we have organic compounds. So living things can use a life force to create these organic compounds, right? And this theory of vitalism existed until it was disproven. So first, it was disproven by Michel Chevreul. And he was basically the soaps man, okay? And he was really a physics and chemistry professor who studied soaps. And he found that you can separate soap into several pure compounds in the lab called fatty acids. Just like those fatty acids that are made up of lipids that we talked about. Yes, he's the one that helped discover that, okay? And this did not require vital life force. He was able to do that in the lab. He took some animal fat, added some sodium hydroxide and some heat. He was able to form soap and glycerin. Then he took that soap strand, for example, added an acid to it, and he was able to create a fatty acid glycerol as well attached. And when you go into biochemistry and organic chemistry, we're going to learn more details about these structures as well, okay? So he was the first one to be like, hey, this is disproven. I didn't have to have a life force in order to get these other organic compounds as products. But because he was using an organic compound to start with, which is animal fat, it didn't really pick up that much heat. Then Frederick Wohler, and I know that you're supposed to have little dot here, so apologies. Frederick Wohler, he's the one that came through in clutch, and he was the one that really was like, there's no way this can be proven because I disproved this so well. And why did he disprove it so well? Well, he was a chemistry professor who was able to convert an inorganic substance, something with quote unquote no life force, right? He was able to convert that into an organic substance. And that completely just disproved vitalism itself. So now you can't just be like, oh, Michel, he had an organic substance and made organic substance, even if it wasn't a lab. No, Friedrich came back and he said, okay, wait a minute. Here's an inorganic substance, ammonium cyanate. I'm going to heat it up a bit. And guess what he was able to form? An organic compound called urea, which is a part of our piss, right? Or P, whatever you want to say. And so this completely disproved the vitalism theory. Now, we can use a definition we have created earlier to continue the knowledge that these scientists have completed. And that's the reason why it's allowed us to be able to go through and have these lectures and do all this stuff, is because of all the work they've done. So just keep that in mind. So why is organic chemistry so essential? Now, I know we can see now. I mean, it's just too ubiquitous, right? So once again, it helps us understand compounds that make up life processes, that's for sure. I mean, it can create synthetic fibers, plastic, artificial sweeteners, drugs, all this kind of stuff. All right. Also, I just want to introduce you to one of our new characters, Carbon Man. This carbon is basically going to be attached to hydrogen, so we know we're dealing with organic compounds. And it has 4 open bonds. This is all based on carbon on the periodic table. Okay, folks? And so this carbon is what makes up drugs in the pharmaceutical world. Okay, it makes up plastics and gases in the petrochemical world. It makes up like Roundup and weed killer in the agrochemical world and pesticides. And it also makes up and is the reason for foods and flavorings and perfume smells, all coming from this compound. And we can go further. These are just basic examples, right? It also will help with our energy that we rely so heavily on to power our entire civilization, right? That's all based on organic materials of coal and petroleum. So there's a lot we can talk about. When it comes to like pharmaceuticals, okay, think about life-saving medications such as antibiotics, painkillers, anti-cancer drugs, whatever you want. The organic chemistry, the pharmaceutical industry definitely relies heavily on organic chemistry to design and synthesize these compounds. Okay, so that's going to improve human health worldwide. Next, let's talk about petrochemicals, or should I say the backbone of all the materials we mainly use. Oil, gas, plastics, fibers, right? Rubber, all that comes from petrochemicals derived from crude oil, which is organic substance, folks. There we go. We also can go further into agrochemicals, like I was talking about. Pesticides, fertilizer, herbicides, so think of Roundup, things like that. These are synthetic compounds that are developed to protect crops from pests and, of course, enhance any kind of productivity in the agricultural world, right? You can kill stuff off, that means you're going to get way better yield. So just think about that. And then finally, again, foods and flavorings. So all the food we have, the preservation techniques, literally you can take a strawberry and take the organic compound that causes the strawberry to smell like strawberry and then use it in fake products like fake strawberry jam. Or like instead of using the jasmine flower and have to press oil, you can just take the organic compound, make a synthetic version of jasmine and spray it all over yourself, like things like that. So the food and flavoring aspect is definitely very important. Also preservation techniques as well, that helps with organic chemistry. So we're talking being able to create flavors, odors, colors, additives, anything that's going to appeal to the culinary experience, meaning appeal to the money and marketers' pockets, right? That's definitely organic chemistry as well. And so if we go back to our definition or whatever definition you came up with to just bring this all in, we know all these compounds are made up of carbon, hydrogen, okay, that potentially can be attached to other carbons, nonmetals, and halogens, encompassing organic chemistry. And the list of these materials can continue. We can talk about biofuels, adhesives, etc., etc. Right? So now that we got our definition of organic chemistry, we got to study the star of the show. We have to study carbon. We got to get more details. We can't just say, oh, carbon concatenate and make all these bonds. We got to get more. So now the star of the show is going to help us introduce carbon man. Okay? We know that carbon is going to be group 4 in the periodic table. So I created carbon man to represent a carbon atom with the ability to make those 4 bonds, as I was telling you earlier. Okay? Now, at this point, you might be saying, I got to get to know about this dicarbonate. It's insane how many organic compounds he can make, right? So I know that you want to get to it. Go ahead and hit the next video to allow you to get more allow you to get a little bit more introduced to him. Okay, folks, again, do not forget this is an introductory portion to organic chemistry. So you're going to learn much more about carbon and what it can do later on in a future course. Good luck.